important for you. Okay. Hope the slide is visible to all of you. Okay. So from chapter 5, one problem. What is IID observations? They are distributed now uniformly. Instead of Gaussian, they are now distributed uniform. So the data, observed data distribution is given to us. Find the sufficient statistics. Write the distribution function. This example we saw while we were discussing sufficient statistics. Almost same example because it's uniform nature. So therefore it's 1 by 2 theta with u of xn plus theta, u of xn minus theta. So what is the distribution for now? 1 by all samples you have to multiply because IID all samples x0, x1. So x0 is uniform, x1 is uniform, x2 is uniform. It is because it's rectangular function. In the first one you wrote like that because they are distributed to minus theta and plus theta. If you have confusion to understand this one, draw a waveform. Okay, minus theta to plus theta, you draw a rectangular function, actually a square function. It is symmetrical, therefore it's xn plus theta minus u of xn minus theta. Product also. So product of all of them, 2 theta power n, product of all of them. So therefore, product is always equal to 0 for xn outside this range. In this range, it is not 0. Outside this range, it is 0. Hence, equivalently, minimum of xn minus theta, maximum of xn less than or equal to theta. Minimum should be more than this value. Maximum should be less than this value. That should be the range of your observed data. Absolute value should be limited to theta because it is minus theta to plus theta. So this is how. Hence, this value becomes 1 by 2 to the power n u theta maximum of x of n multiplied with 1. So you can take it as product. So it is g of t of x theta hx product. You have converted this into product. Therefore, t of x is this function maximum of x of n theta minus t of x. So this is maximum of absolute value of x of n. So this is the sufficient statistics because you could write distribution function into this form g multiplied with h. Here h is assumed to be 1 because there is no xn here. Okay. Coming to another simple example from chapter 6 is again exponential signals observed under noise. R is known constant, A is also unknown value. Now you have to estimate it. Wn is 0 mean white noise. So this is now stated as white noise, not Gaussian. So it is not white Gaussian noise, but it is 0 mean white noise with variance sigma square. What is the difference between white Gaussian and white noise? You know very well. White Gaussian noise has a power spectrum Gaussian. White noise will have power spectrum constant. So recollect that. So now we are asked to find best linear unbiased estimator blue for parameter A. Find its minimum variance, and this minimum variance, does it approach 0 as n tends to infinity? That means is it efficient or not? We have to identify. So you know the definition of blue and take the estimator form directly. H C inverse H inverse, H transpose C inverse of x. So what is H now? Write it AR power n, R power n. Okay, it is a row matrix. You can write as H transpose column matrix 1 R power n minus 1. C theta inverse is sigma square. So A hat is now substitute 1 by sigma square, sigma power R 2n, 1 by sigma square R power n. That is equal to 1 summation R power n divided by summation R power 2 because inverse sigma square gets cancelled away. This is what you saw in previous file, one of the problems. So therefore this is sigma square by r power 2n. So variance tends to 0 if r is more than 1. Because the summation r power 2n, you write it as 1 by 1 minus r square something. And as r increases, the 1 minus r square is insignificant, 1 is insignificant. You can take as r square. So r is increasing. So therefore, 1 by r square will decrease. Slowly it converges to 0. So hence this tends to 0 if r is more than. That means if n equal to 10 to infinity, a power n will also tend to infinity. That means variance tends to 0. From 7, we are given a data set xn, a, sn plus wn. Now you see the terminology, a times s of n. The sn is known and wn is known. Okay, so sn is a signal known to you but weighted by a. So you have to estimate the value of a. So that means true signal is modified with scale factor. It's a linear modification. So it is under h theta plus w. So your linear data model only. Find maximum likelihood estimate. Earlier blue estimate, now maximum likelihood estimate. Suppose you take Sn equal to r power n. You can this solution, you replace Sn with r power n, it becomes maximum likelihood estimate. Compare previous blue estimate and present maximum likelihood estimate. Signal is same. Determine the PDF of estimator and whether it is asymptotic PDF holds good or not, we have to check. So same CRLB extension. So the 1 by 2 by xn minus asn square. So minimize the exponent term. So xn minus asn square brackets to find maximum likelihood estimate. And we take the differential and make it equal to 0 and solve it and find the optimum a. So that is what is done here. So a hat will be xn sn divided by s square n. So this is the maximum likelihood estimate. What is this one? Because average of a product of xn sn, that is a correlation between xn and sn. And summation average of s square, and this is mean square average power of the signal. So one way it is similar to your correlation receiver. Okay, so a PSK signal value amplitude sample value is multiplied with the true value. If it is plus a, it could be minus a. If it is plus a, in phase arm will give you plus a square output, large output. If it is minus a, other arm, quadrature arm will give you large output. So one way is correlation method only. So what is PDF now? Expectation we find first a hat, because you know expectation of this one, expectation of this right hand side. So it is expectation of x of n, expectation of s square n. So e of s square n is same as it is because the true value. Xn is the expectation of xn a plus sn into sn, asn into sn, as square n. So is constant. You can bring it outside. So a into summation of s square n. This get cancelled. It is equal to a. What about variance? Again, find variance. So substitute variance of a hat. A hat is this one. So variance of this right hand side. That means variance of the sum of xn sn divided by variance of sum of s square n. Substitute that one. Variance of xn, some exchange summation variance. Expectation of variance of xn s square n, sigma square s square n, s square n square. So therefore, it is one get cancelled, so this will go away. Sigma square by summation of s square n. Summation of square is average energy. Okay. Earlier it was n for DC signal. Now it is not n. It will become something else. So therefore, sigma square. This is your I inverse of A, inverse of Fisher matrix. Okay. So therefore, for unity energy signal, I mean, what is unity energy signal? Summation of s square n is equal to 1. So for that case, variance is equal to sigma square. That is a true value. All this tells you that the estimator is Gaussian PDF. even though distribution of Sn is not known to you, you can still it is Gaussian. Variance of A hat is Gaussian. Why? It is A is xn minus wn by S of n. Xn and wn is Gaussian. So it's transformation of random variables. So one can easily prove this statement. So A hat is Gaussian since it is linear in data, hence PDF of A hat is now what is the average value A, what is variance I inverse A, that is sigma square. NA I inverse A or NA sigma square. So this asymptotic PDF holds good for finite length data records also. So here n tends to infinity, like that is not there. So without n tending to for small n also, variance is equal to sigma square because of unit energy signal you are selecting. That means plus 1 volt minus 1 volt for PSK amplitude. 8.3. So yeah, now we got directly the signal model is S of n is equal to A for first samples and is minus A for next set of samples. Probably this kind of positive pulse, negative pulse you have discussed in one of the popular topics in digital communications. Can anyone of you remember that signaling? There are so many signaling formats, pulse formats you have studied for baseband data transmission. There's one popular pulse format used in line communications. Anyone of you remember that?
NRA.
Yeah, no. It's not written to 0. Here it is returning to 0. No, negative also is there. Suppose m is n by 2. For half samples it is positive. For half samples, next half samples it is negative. What is that format? Positive, negative, in same symbol interval. Okay. Manchester coding, you forgot so easily. Okay. Positive pulse followed by negative pulse. So that average is 0. DC energy built up on your line is 0. Especially electrical line communication, that is popular. LANs, Manchester code was popular. Ethernet LANs. The reason is that. Okay. See, okay. Anyway, at least one of you remember the names. Find the least square estimate now. For this problem, earlier you saw blue estimate, then you saw maximum likelihood estimate. Now you have to find least squares estimate. Okay, so find the minimum least square error also. It's not minimum mean square error, it is minimum least squares error. Assume that xn is Sn plus Wn and standard. Okay, find the, because it is a least square error is a random variable, it has its own distribution. So find that. So take LSC criterion, J function, xn minus Sn square. So these are risk function. So take derivative, put it 0, solve for A. That is J of A is this one. Theta is equal to A in this example. So A hat is 1 by n, summation of xn was 0 to m minus 1, m to n minus 1 summation. So that means a sample averaging only, but for half samples, summation is 0 to m minus 1, not half. For next m minus n samples, it is some values are different because for here it is A, for here it is minus A. So this is A, this is minus A. So that's why this. So minimum value, if I try to find out now, xn minus A hat, xn minus A hat, xn plus A hat, xn plus A hat, because this is solve this one. So x square n, x square n, x square minus n A hat squared. So now Wn is having variance, so find PDF. Because Wn is white Gaussian noise, 0 mean, expectation of this one will be 1 by n, x square n is a plus wn. So it is 1 by n ma minus na minus ma. Okay. So this is a. What about variance? Substitute 1 by n square variance of xn plus variance of xn for these two sample numbers. So it's variance of xn, m to n minus 1 variance of xn summation. So m sigma square, n minus m sigma square. That means xn you replace with a plus wn. So find out this one. It is sigma square by n times sigma square. Same as your sample averager. There is nothing different, but only thing is you are partitioning that length n into two parts. So 0 to m to n. But it's linear only. So therefore, estimator is Gaussian because linear function in data as per definition. So x of n is Sn plus Wn, a plus Wn or minus a plus Wn. That is why it is linear estimator. PDF would be already found mean and we found variance. So n a sigma square by n. Minimum mean squared error estimator. So each one example for each type of estimate. Data are observed, sample having conditional PDF. So because it is a minimum mean squared error, so conditional PDF is given here. So Pxn condition on theta. So it is a condition on theta. Okay. So a priori condition on theta. The observations are independent. Exponential minus xn minus theta. The x0 condition on theta is independent of x1 condition on theta. So what is the prior PDF? Prior PDF for parameter is exponential. Conditional PDF is exponential. That also exponential. Naturally, xn is theta plus wn. Wn would be xn minus theta. So find the minimum mean square error estimate. For 10.2 chapter, you must have seen problems. Conditional independence, how to define all of that one. So from that, you can derive like this. So you substitute E minus summation of xn minus theta. E minus, you can take it as n into 1 by n of this one. N into 1 by n of this one is sample averager. 1 by n of n theta is theta. So x minus theta, x bar minus theta for all xn's greater than theta. For some variable psi, minimum of xn's greater than theta. Rewritten in this form. So P theta condition on x, this is the a posteriori density. Use Bayes rule, substitute this, and you can get n minus 1, E theta n minus 1, E n minus 1 minus 1. How you expand this? Okay, substituting this and applying Bayes rule. So you have to combine these two, minus n x bar plus n theta minus theta. So combine theta terms, so you will get like this. So theta hat is expectation of this one. Substitute expectation of this. So that is this one. So again, re-expressing this into this form for two limits tau and 0. So this becomes this complicated to be appearance, but once you write it, it's very simple minimizations. Okay, summations and expansions, combining the terms only. So finally, you can prove that is tau En minus 1 tau psi En minus 1 psi minus 1. So substituting the value of psi minimum of xn's greater than theta is what sometimes you take a minimum selector, etc. Okay, so En minus 1 psi, En minus 1 psi. So this is psi times En minus 1. Take the ratio or use as it is, minus 1 by n minus 1. So therefore, minimum mean squared estimator is minimum xn by 1 minus e power n minus 1, minimum of xn. So minimum of xn by 1 minus n minus 1 by combining these two. So en minus 1, so you bring it down. So 1 by 1 minus e of minus n minus 1 minimum of x. So this is the least square estimate. So how do you calculate this one? Observe the data, select the minimum. That means sorting. After sorting, you take it minimum and substitute into this minimum value. So n already you know, substitute, compute this value, compute this value. Chapter 11. So data is observed to be Gaussian here once again. So they are independent. Condition on mu, they are independent of each other. Mean has this variant distribution mu naught sigma square. The mean itself is having distribution. Okay, find minimum mean square error estimator, map estimator. So first minimum mean square estimator. So for prior Gaussian PDF knowledge about helps assume values of mu near to 0 or more probable. And then x condition on mu, substitute this condition. The mu condition on x, substitute, and p minus half of q function, where q function is defined like this. So this is how sigma square is 1 by n by sigma square plus 1 by sigma square, n by sigma square x bar mu by sigma naught square into sigma naught square. So this is how mu and this one both are calculated for the estimate, variance estimate. So the minimum mean square estimator is expectation of this one. It comes into this form. Therefore you can expand this function and it comes to this particular format. This is what you saw earlier, some function of observed data and independent. Second function is independent of observed data represented by alpha. So alpha is a weighting factor. This is sigma mu square by sigma. This variance of mu, that is your mean, and variance of noise divided by n. So therefore, when little data is observed, sigma mu square is smaller than sigma square by n. Alpha is so small. Therefore, this converges to mu naught. But suppose more data is observed, sigma mu square now is more than sigma square by n. So therefore, this value is significant. So the alpha is also almost large. Therefore, this closes to, that means typically sample average. So minimum mean square estimator simply becomes a mean value or sometimes average of all the mean of the known quantity. So problem, your mean, xn's are independent condition on mu, where mu is the parameter to be estimated. So it has its own values, average value and variance value. It is depending on all of them. Alpha is depending on all of them. So it is, therefore it is not equal to sample mean x bar. It is something else. X bar scaled plus added. But under some condition, when you observe it, that means n is quite large, n is quite small. If n is small, sigma mu square is smaller than sigma square. Therefore, alpha is tending to 0. From that, one can see that estimate value converges to true value, mu naught, true value of the mean. If it is large, then it is average. That means your minimum mean square estimator is replaced by sample average. Computation is very simple. Weighting factor also depends on a priori knowledge. It depends on this prior knowledge. It depends on the data knowledge. So map estimator also can be found with posterior PDF represented like this. Map estimator is from these examples. One can a less than equal to a naught, a greater than equal to a naught. Why a naught means you took it as mu naught. Okay, the mean value is mu naught. So the parameter is A, or A naught and mu naught are same. Okay, so the map estimate of mu or A, denominator normalizing factor do not depend on mu. So sigma square average. So limits are minus A naught to plus A naught. This is how it becomes minus A naught when average is less than this. It becomes average in this limit, minus A naught to plus A naught. Plus A naught is more than A naught. So this is smaller than a true value. So it is between minus 1 plus, and it is more than true value. So therefore, here in this example, computation is very simple. So easy to determine. Doesn't no integration, nothing, no only some kind of maximization only. So minimum mean square error estimator is difficult to obtain because you need to do some integration and obtain these values, mu, alpha values, all these things. So minimum mean square or map estimator, both are same, identical, if both are jointly Gaussian. Okay. Linear minimum mean square error estimator. Please bear for 2-3 minutes. I am closing this end of the chapter exercises because next week I am not taking classes. I will the next class I will have to finish Kalman filter. Observed data. Sn and Wn are zero mean, wide sense, stationary random process, uncorrelated to each other. Signal and noise are uncorrelated. They have their own autocorrelation functions. So from this you can observe that autocorrelation functions are delta functions. That means they are all IIDs, independent data samples. So signal samples Sn's are independent of each other, Wn's are also independent of each other. Jointly they are wide sense stationary process. So determine the minimum mean square error estimator for the signal component based on the observations x0, x1 to xn minus 1 and corresponding matrix also. So least mean square estimator is obtained from the CSX multiplied with CXX inverse of x. This is the estimator. We have developed this. So that means typically C of XX is expectation XX transpose. That is RXXK because all are uncorrelated. RSSK plus RWW linear. So RSS plus algebraically you can write like this: matrix sigma S square, matrix sigma square. Variance of signal plus variance of this one. I is idempotent. CSX cross covariance between S component and X component. This is what exactly your correlation receiver computes. S X transpose, substitute, this becomes RSS because expectation W is 0, so it is sigma S square. So substitute this into this, it is RSS into RSS plus RWW inverse of X. So it is nothing but some W of X. So all this is W. But this matrix is Wiener smoothing matrix. So vector estimator is least mean square minimum mean square error estimator, linear minimum mean square error estimator is substitute this one, so it comes to sigma S square by sigma S square plus sigma square. Hence, estimated signal is this multiplied with x of n. So minimum Bayesian estimator is this substitute. So compute this one, so it becomes sigma S square by. So this is a minimum Bayesian mean square error estimator. With this, I am stopping my discussion. So some 1 or 2 problems from each chapter I have taken to solve for all types of estimators we have discussed so far. Please go through your textbook and simultaneously with this presentation, then you can easily understand all these computations.